It's a great pleasure to give you here in the audience an overview of possible fuels that we have today and that we might and will have in the future. So to start with here, I brought along one slide that shows all different kinds of fuels that we can possibly think of, basically structured into three areas. So we do have here in black some fuels that are fossil based. Then we have in green on the right hand side actually fuels that come from biomass. And then the topic or the fuel that are currently mostly in discussion are the e-fuels that are derived and generated from renewable energy. And I will guide you through this slide. I will start on the left-hand side. I'm quite sure that everybody is well aware of that. So very conventional, we do have the oil. We can refine the oil to produce gasoline and diesel, also heavy fuel oil for marine applications and so on. Then from natural gas, we can generate methane. It is actually methane, compressed natural gas, lean liquid natural gas. And then also via coal. This is a long time ago that was done more often. Today, not so much anymore. From coal, we can generate syngas. And from that, we can generate actually also hydrogen. And then we can also generate synthetic fuels such as gas to liquid or coal to liquid with beneficial fuel properties. If we then look into the biofuels, we can do different stuff with biomass for sure. We can extract it and then get vegetable oil. We can do fermentation to get to alcohols, or we can do anaerobic digestion to get into methane and then also produce different methane variants. Then also what can be done from biomass is it can be gasified, it can go into syngas, and then by synthesis, mostly Fischer-Tropsch synthesis, we can actually generate also biomass to liquid, which are then liquid fuels, which have a quite similar chemical structure than we have in GTL or CTL, and we can use it in different kinds of engines. Then, and that is the topic I would like to focus on mostly, we are talking about the e-fuels. And for e-fuels, we use renewable electric energy. So that is for sure what we want to do in the future, to use renewable electric energy. Then we generate syngas by electrolysis, and we also use CO2. And then from the syngas, actually the synthesis can be done. And then we arrive at PTL, which is power to liquid, which are the fuels that we are really looking into for the future. Now, I said I would like to focus on the e-fuels, and so I will go on the next slide into a more closer discussion of the power to liquid fuels. And you can see that actually here, these are paraffinic fuels that are produced by converting electricity into hydrogen. We combine it with CO2, and then we get liquid fuels. And very briefly, I would like to show you how that process looks like. So in the very beginning, based on water and electricity, by using electrolysis, we generate actually the hydrogen. And this is done by different configurations or different technologies. And today we do see an efficiency of generating hydrogen by this of roughly 65%. In the future, there's still also potential to increase this, to improve the efficiency. So then it could be later on, there will be also efficiencies up to 75% or even more. This is really also still in the stage of development. Yeah, by doing the electrolysis, we actually get into hydrogen and oxygen. And then later on, based on this, actually the syngas is produced. The syngas is consisting out of hydrogen and carbon monoxide. And this is the water gas shift reaction, which is used to really produce the syngas. And then with the syngas, it can be taken to generate via the methanol route or the Fischer-Tropsch route, which is a well-known technology. Actually, liquid fuels can then be generated. And later on, these liquid fuels then can be post-processed in a refinery to really get into the properties of fuels that we would like to have. So these fuels can be tailored also in a way that they can directly be used for gasoline and diesel, which is the big benefit of this. And we will see in the upcoming slides some more information on this. Okay, so what are the fuels in more detail that come out of this? Before I clustered them as PTO, power to liquid. Now here you can see an overview of these fuels. And I will go through that quite quickly. For sure, again, we need the CO2 that comes from industry today. In the future, maybe also direct air capture or from biomass. On the other side, we need the renewable energy or electricity. And then fuels are possible, such as hydrogenated vegetable oil, methane, ethanol, methanol, the Fischer-Tropsch fuels, paraffins that I just described. And we can also directly use, for sure, the hydrogen. We can use ammonia, it was mentioned before. And based on methanol, there are even further possibilities that can be used. So maybe just very quickly, the HVO, the hydrogenated vegetable oil, at least in Europe, will be ramped down because in the future, we do not want to use palm oil anymore. Then we have the methanol to gasoline, which is a gasoline fuel. Then we have the DME, which is the dimethyl ether, which is the diesel fuel. We have OME, which is also very expensive and difficult to produce. So this is in a development stage. We have butanol, which is a drop-in or a blend fuel for gasoline passenger cars. And therefore, in this lecture here, I would like to focus actually on methane, on methanol, on Fischer-Tropsch fuels, and also hydrogen and ammonia, and go a little bit into more detail of these fuels. Yeah, and I will start actually with the hydrogen. Everybody is talking about hydrogen. It is the most important energy carrier of the future once we have sufficient electricity available. And to go to that, you can actually, or we do know that hydrogen is the easiest and cheapest renewable chemical energy carrier because it comes directly out of the electrolysis. It is already widely used, but for sure there are also some drawbacks. And this is especially the low volumetric energy density. This means that mostly the hydrogen will be stored in a liquefied way at minus 253 degrees centigrade. And then it can be stored, for example, on ships. But because of the still lower volumetric efficiency, this will also consume some storage capacity on the carriers. So just as an example, Kawasaki at the moment is developing and building a ship that will be operated by liquid hydrogen. And this is planned to go into deep sea in the next years. There are also some other announced ships that will be built to actually be operated and transport hydrogen. Yeah, so hydrogen for sure has no carbon inside. So here, really, this is the fuel to go with if we want to achieve well-to-wake 0 grams per 0 grams of CO2. And really, this is the most important fuel when we look into the future. But it also has some drawbacks because it is gaseous and not as easy to store. I mentioned that before. And today also, it is very rare in application. And we made a small matrix to have a look at the benefits and drawbacks. So the fuel costs, once we can generate sufficient e-fuels, are beneficial. The availability today is, let's say, medium. It is a well-known chemical, but not widely used in transportation or transport. The technology readiness level for fuel production is rather good. The fuel distribution today in harbors is very low. And therefore, there are still some areas where for hydrogen usage, really some improvements are needed. Then next up, I would like to go into ammonia. We heard about that before. Ammonia is a fuel that was actually used before. Here in the Second World War, on the left-hand side, you can see a bus which was operated with ammonia. So what is ammonia about? Ammonia really has the very big benefit that it does not need any carbon. So nitrogen is much more easy to obtain than carbon dioxide to produce carbon. And that is really, when we want to go into a carbon-free future, really the fuel that has a lot of benefits. Again, here there are some drawbacks because the ammonia is very reluctant to ignition. So this means we really have to investigate new ignition systems. It also produces, because it contains nitrogen, a lot of NOx. So therefore here, a lot of development work is still needed. Yeah, but on the other side, it is an established product that is actually well known for fertilizers, for example. And that is also on the negative side, it is toxic to human and to sea life, also at very low concentrations. So that is something that also has to be dealt with. Yeah, on the metrics down here, the fuel costs can be produced at rather attractive costs. The availability today is still rather low in large amounts. The technology readiness level, if we need to develop also the technology for the engines, is rather low. Fuel distribution is also not given at the moment. Yeah, and the compatibility with available vehicles and engines is also not really given. Additionally, and I will come to that later, ammonia could also be one possible energy carrier if in the future energy is transported from regions to other regions, for example, from the MENA region to Europe, then it could be that hydrogen is transferred or converted into ammonia because it is more easy to transport, and I will talk about this a little later. Yeah, we get to natural gas. Natural gas is a very well-known product. It is well used also in applications in vehicles in different forms. It is available today already in 100 harbors, so the availability there is also quite good. And we know that for sure the natural gas has a roughly 15% lower CO2 emissions compared to diesel and is directly now available in large amounts. Yeah, and you can see here an example engine on the left-hand side, and with CNG. Today, if we look into emission legislations, yeah, it is possible to achieve also very low emissions. It is really a well-known technology. So therefore, natural gas is a cost-competitive fuel today. In the future, it can not only be produced also from as biomethane from biomass, but also as e-methane, and could therefore be also a CO2 neutral fuel in the future. Then today we see for a methane engine, for a CNG engine, there are additional hardware costs. They are often compensated by some incentives, so that is attractive. And like I mentioned before, the natural gas grid is well established worldwide, which makes it a fuel that is well available and well known. And here in the matrix, we separated a little bit between methane and methane that is produced actually from renewable sources. And you can see the fuel costs are very attractive. The availability is also attractive. In the future, it will be also more attractive if it comes from renewable sources. Technology readiness level is very good. The fuel distribution is very good. And it is very well known how engines have to be adjusted that they can actually be operated with natural gas. For sure, some updates, some adjustments have to be made. Yeah, we get to methanol. Methanol is already an established platform molecule that is very well known in the chemical industry. It is also used for fuel already, and it is an excellent fuel. We will hear also later in these lectures how methanol can actually be used in an engine in different ways. Yeah, and we do already see some applications on the sea. So today, there are roughly 5 methanol powered tankers that are on the oceans already, and roughly 5 more are currently being built. So that is really a fuel that comes more and more. Yeah, and you can achieve for sure also with methanol very low particle emissions. And our methanol is very well known, like I said, and it is available in harbors today, also around the world. Over 100 harbors actually do have methanol available. So this makes it well in the infrastructure to be used in shipment. Then methanol is very easy to produce. It is, let's say, the easiest producible renewable liquid energy carrier because it's the first step that comes after the hydrogen. If we produce a liquid fuel, the handling and infrastructure is still considered to be a little bit complex because also here we have a toxicity issue. And also we have some properties like an invisible flame. These are issues that have to be worked on. And then for sure, the applications are quite limited. I mentioned some numbers, but there's really a big push from shipping agents and legislation. And particularly this is coming from Asia. And therefore, this will also play a major role in the future of fuels. Fuel costs, like I said, are very beneficial. Availability also. Technology readiness level, like I said, we will show this a little bit later, also is also beneficial. And fuel distribution also. For sure, the fuel is not directly compatible with available engines and vehicles, but it is quite well known what adjustments have to be done in order to actually make this a working fuel. And as I mentioned for ammonia, that it could possibly be a fuel that is actually in the future transporting energy into Europe, for example, but also to other regions around the world. This could also be methanol. So methanol is also a potential energy carrier for the future. Then we get into Fischer-Tropsch. I mentioned that before. Fischer-Tropsch is very expensive and very, very energy intensive when you want to produce it, but it has the very big benefit that Fischer-Tropsch fuels can be tailored in a way that they meet today's fuels legislations or norms and can directly be used in available engines. And if it comes down to the fact that we really need to make such a fuel available in many places, then it is for sure very beneficial to have a drop-in fuel that can substitute parts of the available fossil fuel. And for example, if we talk about total cost of ownership, I forgot to mention that on the slide on methanol, where really it is very important to have cheap fuel, attractive fuel. This will be more a fuel that really needs to be available around the world. As a drop-in fuel, it is more expensive. And therefore, for example, in yachting, this could be a fuel which is actually being used. Yeah, I think most of the other points on the right-hand side I mentioned. So the fuel costs are the disadvantages, very intensive in energy and costs. I mentioned that. The availability is medium, could be good because it's a drop-in fuel. The technology readiness level is for sure very good because these fuels are just substituting. The fuel distribution, therefore, can also be good. And the compatibility with the existing engines and vehicles, therefore, are also extremely attractive for such kinds of fuels. So you can already see here that, again, like Andreas Viatala mentioned before, there is not the one fuel that will make it in the future, but it's really depending on the application, what fuel is most beneficial for what. Okay, then that was a short introduction into the different possible fuels. The question for sure arises, will we have enough fuels in the future? And here you can see actually a graph on the left-hand side that comes from Fuels Europe, which is actually the collaboration of the different oil companies in Europe. And they have started to analyze at what time is how much invest needed to achieve the required amount of diesel substitute. So what you can see here, until the year 2050, according to this scenario, we will need around 150 million tons of oil equivalent to substitute really the fossil fuels. And this is for sure to be seen in connection with also electrification. But if that can be achieved, then by 2050, roughly 100% of the road transport and 50% of aviation and maritime transport could be emission free. But this would at the same time also require immense invest, up to 650 billion euros, to make these factories, these plants really available. And you can see on the right-hand side, that is a pilot plant that is currently being built up in Chile by the companies Porsche, Siemens Energy, and ExxonMobil. They are setting up a company that produces hydrogen and then later on produces methanol. And they are planning to produce already in the next year 130 liters of e-fuels and so on. And they will use it on site or in areas around the plant, but also for sports, for sport races, for sports car racing. This is supposed to be used in this pilot stage. Saudi Aramco is also at the moment building up such a plant, and they are planning to start production in the year 2023 and 24. So there are actually possibilities and plans to set up these plants. For sure, they will need roughly 5 to 7 years until they are really operational. But there is overall in the assessment that we can see here, it would be or will be possible if really the right incentives are given and the investments are being done to get to the amounts required to be CO2 neutral as much as possible in the year 2050. Yeah, this would be the reduction actually of CO2 or the availability of e-fuels. The question then is still, where do they come from? How do we get the energy? And on this slide here, you can actually see that. You can see on the left-hand side on top, you can see the power, the wind power density, and you can see where actually wind power is very beneficial. So you can see that for sure at the coast, but also in Greenland, there a lot of wind could be used to generate electricity. And then for sure, photovoltaic electricity output. And I think you all know that if you go into North America or the Middle East to the MENA states, there's really a lot of solar energy available. And then if you make an assessment how much of the land area is used to generate enough electricity, to generate enough e-fuels, then you get to some numbers which are quite impressive. Because if you really have a look at that, then the 0.3% of the world's landscape or 1% of today's agricultural area would be sufficient to generate enough e-fuels by the year 2020. So it is not impossible. There is a pathway to do it, but the right boundaries have to be given and the right investments have to be taken. Going to the next slide, that is also very important. What are the costs that we assume for e-fuels? And on the left-hand side, you can see if we produce e-fuels, hydrogen, then methanol and Fischer-Tropsch. And this is an assumption for 2025. And it is assumed that in the year 2025, the hydrogen per liter diesel equivalent would cost in the production roughly 90 cents. While the methanol, if we do need to do some post-processing and conversion, would cost 1.34 euros, and then Fischer-Tropsch, I mentioned more expensive, would cost 1.67 euros. And if you compare that to today's diesel, which is roughly 0.5 euros, you can see we are not way off the costs. And for sure, with the right support from politics and so on, there is a path to really get that going and to really make that working in the future. Yeah, the right side of this picture actually shows how the e-fuels are being produced. This is an example from Germany. Today, if you want to produce really CO2 neutral fuels that are accredited by the politics, you have to produce the fuel off-grid. So this means the electricity production cannot be connected to the general grid. This is the first stage. Later on, for sure, the electricity generation needs to be connected to the general grid. And also then the CO2 can come from whatever resource to produce actually the carbon neutral fuels. And then I mentioned that before, another possibility then would be for sure the production of e-fuels outside of Europe or Japan or US in areas where we really have enough sun to generate electricity. Then for sure it is also the option to transport electricity and energy across the ocean. And you can see that on the next slide, how that looks like and what are actually the numbers connected to that. So today, and you please look into the middle on top, Saudi Arabia to Germany. This is a scenario where we estimated together with some other facilities, what actually would be the cost of transporting energy from, let's say from the Middle East into Germany. And what you can see in this diagram on the very left column, you can see that it would be, or it is the cheapest to produce the hydrogen with roughly 15 euros per gigajoule. But then there are additional distribution costs. So the hydrogen needs to be liquefied, it needs to be transported. And these distribution costs actually lead to costs by 2030 of roughly 30 euros per gigajoule. And then on the right-hand side, you can then see how that looks like for methanol. And for methanol, we have higher costs to produce the fuel. I showed that before. But because it's liquid, it is easy to transport. There are very, very small costs that are connected to the distribution. And so you can see that actually the costs for getting hydrogen over is on the same level than getting methanol over. I think that is the most important message here. To get that over is the possibility to do it either in methanol or in hydrogen. Could also be ammonia. But you can see how that could possibly look like to transport energy from different regions around the world to regions where it is actually needed in large amounts. I just gave the example of Saudi Arabia into Germany. So let's get to the very final slide. What we always try to do is to condense the information. And you can see that here for the fuels that I mentioned in different categories. For sure, this always leads to a lot of discussions if all of these ratings are okay. So if there's a bold or a fully gray circle here, that means it's good, it's positive, it's beneficial. And if it's not so filled out, then there are still drawbacks. And just as an example, if you look here for hydrogen, then you can see here it is for sure very beneficial with regard to greenhouse gas emissions, to local emissions, but the invest that is required into converting, into producing hydrogen, into storing it is very high. And so you could go now through all of these fuels. I will skip that here now and see that there is, again, not the one fuel that matches it all. So no one fits all, but it really has to be looked at what is beneficial for what application. And for sure, I showed you a little bit the pathway into getting these fuels. Where do they come from? And for sure, the real or the right boundary conditions have to be achieved to also give the right value to people who want to actually be part of the value chain. So this has to be attractive also from a commercial point of view. And then I'm personally very convinced this can be a very important part of getting into the CO2 neutral future. So this concludes my part of the presentation. I thank you very much for your interest, for your patience. And if there are any questions, for sure you can ask them now. And therefore, I will hand it back over to Max. Thank you very much.